Next we have lemma 696. This one says that for any matrix A in the matrix algebra Fn, the determinant of A is the same as the determinant of its transpose. Now we know that we obtain the transpose of a matrix by interchanging its rows and columns. So interchanging rows and columns does not change the determinant of a matrix. And because of this fact, all the previous lemmas, these lemmas that were related to the rows of a matrix and determinants will have their corresponding column versions. Let us recall one of them and see how it looks. Look at this determinant. The matrix here is a 3 by 3 matrix whose entries you can see, and you can see that the entries in the first column are multiples of 2 of some numbers, which are actually 1, 2 and 3. Now we know that if a similar thing happens with a row, then we can take that 2 outside the determinant and calculate the determinant of the resulting matrix, multiply that by 2, that will give us the determinant. Are we able to do a similar thing with this matrix? Here, however, that thing is happening in the first column. Yes, we can, because of what we saw right now. So what you do, in place of the matrix, you write its transpose. So the first column becomes the first row, 2 times 1, 2 times 2, 2 times 3. The second column becomes the second row. You already know these things, 3, 4, 5, 3, 4, 5. And the third column becomes the third row, 4, 5, 6. And now here you have that thing happening in the first row. So by one of the previous lemmas, you can take the 2 outside because it's a row operation. And that way you have this matrix now. Now in its place, again you can apply the lemma and write its transpose. So 1, 2, 3, this first row will become first column. 3, 4, 5 will become second column, and 4, 5, 6 will become the third column. So now you look at this one and this one. They are almost the same, except that we do not have the 2's here. You can check for yourself. 1, 3, 4, 1, 3, 4, 2, 4, 5, 2, 4, 5, 3, 5, 6, 3, 5, 6. So like that, the other row operations, I mean the other lemmas which involve the other row operations, have their corresponding column versions. Next we have this theorem 692, which you may be familiar with. It has this familiar name also, Cramer's rule. It's a rule that lets you solve systems of linear equations. So you consider a system of linear equation like this, where the unknowns are these xi's, where I varies from 1 to n, and the coefficient of the ith unknown, or rather I should say the jth unknown, say xj, in the ith equation is alpha ij. For example, the coefficient of x1 in the first equation is alpha 1, 1. The coefficient of x1 in the nth equation is alpha n1, and the number of equations is the same as the number of unknowns. There are n unknowns, there are n equations. And on the right hand side you have some filled elements, these betas. Now, if the determinant delta of this system is non-zero, we will see what the determinant of a system of linear equations even means. We will see that. But for now, let's just see what the statement is. If the determinant is non-zero, then the solution of this system is given by these expressions. Each xi is equal to delta I divided by delta. What is delta I? Let me write that. Where delta I is the determinant obtained from delta. Delta itself is a determinant. What determinant it is, that we will see afterwards. But whatever determinant delta is, that itself will give you delta I if you replace the ith column of this determinant with these betas. That is delta I. Now, in order to understand this entire thing, the best thing to do is to look at an example, and that's what we are going to do now. So as an example, you consider this system of 3 linear equations in 3 unknowns, x1, x2 and x3. and the equations are x1 plus 2x2 plus 3x3 equal to minus 5. So here beta 1 is minus 5. 2x1 plus x2 plus x3 equal to minus 7 and x1 plus x2 plus x3 equal to 0. Now, for such a given system of equations, you first of all have a matrix. The matrix of the system is this, or which is also known as the coefficient matrix. It consists of the coefficients arranged in that same manner in this matrix. 1, 2 and 3 form the first row of this matrix. The second row is 2, 1, 1 and the third row is 1, 1, 1. And the determinant of this matrix is the determinant of the system. That is our delta, which in this case is 1. I mean, if you apply the school formula for calculating this determinant, you will get 1, which is not equal to 0. So by Cramer's rule, we can now write the solutions. And let's see in this case what those delta i's are. Delta 1, delta 2 and delta 3. So by the Cramer's rule, the solutions are given by this. I need to write x3, but let us first see what x1 and x2 are. So delta I divided by delta. Delta actually is 1, so I could have not written it also. But I am just simply showing how the formula works in this specific case. So I am writing 1 divided by delta, and this is delta 1. What was the description of delta 1? Delta 1 is obtained from delta by replacing the first column of delta by those right hand side filled elements. If you recall, I mean if you go back to the original system, those right hand side numbers are minus 5, minus 7 and 0. So you can see that in this matrix, we have replaced the first column by those elements. The remaining entries are the same, and well, I could have written determinant of this matrix. However, in order to save space, I am using this vertical bar notation for determinant, which you already know from school. If you write like this, it means determinant of that matrix whose entries are like this. Similarly, x2 is delta 2 divided by delta. Delta 2 is obtained from this by replacing the second column with those numbers. So you can see that the first and third columns are unchanged. 1, 2, 1, 1, 2, 1, 3, 1, 1, 3, 1, 1. But in the second column, we have those numbers, minus 5, minus 7 and 0. And next let us see x3. And this is x3. Again 1 over delta, but here we have delta 3. Where if you go back and see the matrix of coefficients, the first column is 1, 2, 1 and the second column is 2, 1, 1. But the third column is replaced by these numbers, minus 5, minus 7 and 0. So this is what I want you to do. You have the system of equations with you and you can calculate these values actually. Delta well is 1, so you just have to apply your school formula to calculate these determinants. You please do the calculation and see if you are really getting a solution which satisfies the three equations simultaneously. And next we have this result with which we are actually already familiar from school, but now we have it for general n by n matrices over any field F. So for any such matrix A is invertible if and only if its determinant is a non-zero field element. Do not forget that you have to see the proofs of these results, okay, which I am skipping because you can see the proof for yourself. The proofs are available in the text. If you have any doubt, then please let me know. We can then discuss the proofs. So here we are just going on seeing the results, and once this gets over, we will start solving the exercises. This next lemma 697 is about the relationship between the determinant of a matrix and its characteristic roots. For a matrix A in Fn, its determinant is the product of its characteristic roots counting multiplicities. For example, say you have a 3 by 3 matrix where the characteristic roots are 1 and 2, and 2 appears 2 times, then the determinant will be 2 times 2 times 1. So the number of times a characteristic root appears, that has to be counted. Next we have this definition in which, say you have a matrix A in Fn, then for this matrix we define the polynomial determinant of x minus a in this polynomial ring Fx to be the secular equation of A. There are quite a few things to understand here. First of all, I don't really understand why the author is calling this polynomial an equation, secular equation. But leaving that aside, it's just a name, okay? Let us concentrate on this object, determinant of x difference A. And let's try to understand this with an example. For the sake of simplicity, I have taken a 2 by 2 matrix A here, whose entries are 1, minus 1, 0, 1. Now what is x minus A? X minus A of course does not mean that we are subtracting the matrix A from the variable x, which does not make any sense. Instead, what it really means is this: x times the 2 by 2 identity matrix is what we mean by x. Instead of every time writing xi2, we just simply write x, and from context we understand what the size of this identity matrix is. Here A is 2 by 2, so that is also 2 by 2 identity matrix. And if you calculate this thing, this is what you get. What is xi2? xi2 will be that diagonal matrix where the leading diagonal has both its entries equal to x. Elsewhere, of course, it's 0. From that you subtract A, and this is what you get. The determinant of this, you can apply your school formula, this times this minus this times this, is x minus 1 whole square. So that's how this is a polynomial in this polynomial ring Fx, x minus 1 whole square. That for some reason the author is calling the secular equation. We are not talking about this equation. This polynomial itself is being called the secular equation of that matrix A. Now note one subtle thing here. In fact, actually this is what you have done many times in school, but still let us see one subtle thing. We have defined the determinant of matrices whose entries are filled elements. Here, however, we are calculating the determinant of this matrix where the entries are not exactly filled elements, but rather they are polynomials coming from this ring, and this is not a field. This is a commutative ring with unit element, but this is not a field. So in spite of that, the determinant for such matrices also are defined similarly, similar to how we define determinants of matrices with entries which are field elements. Okay, so that is the secular equation of a matrix A. And this is the result about secular equations and how they can be used to calculate characteristic roots of a matrix. So you have a matrix A in Fn, then the characteristic roots of A are the roots with correct multiplicities of the secular equation. This is a polynomial, and polynomials have roots, and which are precisely those field elements where a polynomial, I mean if you evaluate it at that element, you get 0 of A. And in fact, this is what you have used countless times to calculate characteristic roots of actual concrete matrices. And in fact, if you equate this polynomial to 0, you get an equation, really, which is an equation, and that equation is solved for finding the characteristic roots. And that equation you have called somewhere characteristic equation of a matrix. And finally, you have theorem 695, which has a name also. It's called the Cayley-Hamilton theorem. It tells us that every matrix A in Fn satisfies its own secular equation. What does it mean? It means that if you replace x with A, you are going to get the n by n 0 matrix. It's a little misleading if you think of replacing x with A here itself. What it really means is that first you find that polynomial, like what we did in that example, x minus 1 whole square. Then in place of x, if we write the matrix A, then we are going to get a polynomial expression in that matrix. If you simplify that, you will get the n by n 0 matrix. And with that, this section ends. And after that, exercises will start, which we will start in the next linear algebra video. So see you in the next video with exercises and their solutions. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.